Hello, I am Justin Huey, and I'm doing problem 239 from the textbook, in which you are presented with a neutral conducting sphere that has two cavities hollowed out from it, one of radius A, one of radius B respectively. And the one of radius A, they placed a point charge of QA, and the one of radius B, there's a point charge placed in the center of QB. And in part A of this question, we are asked to find the surface charge densities sigma A, sigma B, and sigma big R. In which sigma is the charge density, so we have charge over area, and of course the area of a sphere is equal to 4 pi times the radius squared. So to begin with, we'll start with sigma A. So what is the charge density of this surface right here? Well, because this is a neutral conductor, in order to stay neutral, this charge QA here is inducing an equal and opposite charge around the surface right here of magnitude, which would be negative QA. So sigma A is very simply equal to negative QA over 4 pi A squared. And the same holds true for QB. QB is also inducing an opposite, or at least we don't know if it's negative, but we know it's an opposite charge around the surface here to deal with this point charge. So sigma B is very simply negative QB over 4 pi B squared. And for sigma R, it's a little more complicated. So we know that this surface should be neutral, or all the charge should at least lie on the surface. But some of these charges were pulled away in order to account for these point charges in the cavities. So that's leaving whatever we would have. So that would leave a charge here, and we'll call this positive, to ensure the conductor stays neutral. So let's go through all the way around, like so. And so we have sigma big R of the entire thing, which is equal to QA plus QB, because that's the charge that's technically the opposite of the charges that were taken. Negative QA was taken here, negative QB was taken here, leaving us QA and QB along this surface over the whole thing, which is 4 pi big R squared. And this is what we get for part A. All right, so now before continuing, let me just circle our answers from previous. All right, so now in part B, we are asked to find the electric field outside the conductor. So what's E out equal to? All right, so now to find this out, we'll begin with the electric field definition, using electric field for a point charge, Q over R squared in the R hat direction. And so just applying this to our situation we got here, right now we only care about this distribution right here. The point charge and this little distribution will cancel. Point charge, this distribution cancel each other out concerning the outside effects of the electric field. So we'll only be taking consideration this, which we found with our sigma R earlier. So we'll have 1 over 4 pi epsilon naught QA plus QB, all of that over big R squared, or no, I believe it'd be little r squared actually, my apologies. It'd be little r squared because it's dependent on the distance, it's not at a constant distance. And we know it's in the R hat direction due to the spherical symmetry coming out. It could only be radial. And this is our electric field out for part B. All right, now for part C of this problem, we are asked to find the electric fields of each cavity. So let's continue on this paper right here. Okay, so we know for each cavity it'd be a similar thing because we have the point charge inside. So electric field A, or we're just going to call it electric field A, is equal to 1 over 4 pi epsilon naught QA over RA squared. And we're calling it RA because it's not equal to the radius, but we're calling the vector here a vector inside the cavity going not quite to the outside. We're going to call that our RA, and we'll do a very similar thing for RB when we get to it. So it's coming from the center of the cavity. And then it's also going to be in the RA direction. For the same example I explained earlier, the spherical symmetry, it's going to be in the radial direction. And EB is going to be a very similar thing. 1 over 4 pi epsilon naught QB, the point charge, over radius B, once again coming from the center of cavity B. And that one's going to be in the RB direction. So there we go for part C. All right, now for part D, we're asked to find what are the forces on QA and QB. All right, so the force comes from the interaction between the electric field and the charge. And if you look at our diagram once again, you could see that the electric field generated by QA will actually terminate on the, will terminate before leaving the cavity, and the same for electric field B. So there's no electric field going through here to have any interactions between the two. So by observing that, we're able to say that the force on each of them have to be 0 because there's no outside electric field acting on either of them. There you go. All right, so now for part E, we're being asked, what if we introduced a QC on the outside, a third point charge, if it was brought near the conductor? So what we can show is that, let's just say we put a QC right here, and now we go through A, B, C, D to see what changes. All right, so beginning with A, our charge densities. QA, QB are inside the conductor. They will not be affected. Sigma A, sigma R. Sigma A, sigma B are inside the conductor. They will not be infected. They will not be affected. Sigma R, on the other hand, which existed to account for, to compensate for QA and QB, now has another charge to compensate for. So sigma R will be changed to be equal to QA, QB minus QC to keep the equilibrium, and it'll still be over 4 pi r squared. All right, so moving on to the next ones. Let's see. Okay, part B, the E out will change. The electric force outside will change. As before, as you saw, because we changed the charge density, just as the charge is counted for here, that will change. So E out will be equal to 1 over 4 pi epsilon naught QA plus QB minus QC over 4 pi little r squared, r hat direction once again. And then on to D. Then on to C. No effect on these, still no electric field inside the conductor. That would make a difference here. And the forces, once again, that would have no effect. And that does it for problem 2.39. Thank you for your time.